So why don't you put this thing on, and then I'm going to make a little announcement and an introduction. Oh, and we should actually unmute this time. Testing. Okay, there we go. Can you put that on? All right. Okay, everyone, we're going to get started. So please remember that your project milestone report is due today at 11:59 p.m., so please be sure to get that in. So today we're going to have our next guest speaker, Mohammed Narouzi from Google Brain. And Mohammed will tell us about entropy, relative entropy, and some connections between reinforcement learning and supervised learning.
Hello, everyone. I'm going to talk about entropy, relative entropy, reinforcement learning, and supervised learning. Kind of a soup of these topics. And I just want to start by acknowledging my collaborators. This is based on a bunch of papers with various subsets of these folks on the slide, mainly Ophir Nacham and Dale Schurmans. They contributed a lot of the ideas to most of these papers. Ophir was a brain resident last year in Google Brain, and now he's a research scientist. I take this opportunity to ask you guys to apply to brain residency. This year is called Google AI residency, but it's the same concept. And Kelvin was a resident as well, and I think now he's at UC Berkeley. The talk is basically chunked into 4 chapters, each of which is related to one of these papers. The first part is about supervised learning, drawing ideas from reinforcement learning, and then we'll talk about reinforcement learning first in the very simple setting, more like a contextual bandit setup with a tree action, and then we'll talk about reinforcement learning afterwards. So one of the themes of my research is on the interaction between reinforcement learning and supervised learning. When I embarked on the PhD program a few years ago, usually in machine learning courses, people and instructors would skip the reinforcement learning part. And we didn't have the luxury of having a reinforcement learning course as part of our program. But over the years, we see more involvement of machine learning researchers in reinforcement learning. It used to be that there's just a clique of people working on reinforcement learning and a clique of people working on the rest of machine learning. But I want to talk about the interactions between the two fields, and I want to see more dialogue between reinforcement learning and supervised learning. We can learn from reinforcement learning and apply some of the ideas to supervised learning and vice versa. Actually, when I went over the pattern recognition book by Chris Bishop, I only found 3 references to reinforcement learning. And also, when you look at the references in the reinforcement learning book by Sutton and Bartow, you don't see a lot of references to references of Chris Bishop's book. So we really want to combine these areas and come up with better algorithms and solutions. Okay, what are the similarities? Both of the approaches learn an optimal mapping of inputs states to outputs actions, right? And these days, we use neural networks to do the mapping. In supervised learning, we have access to the optimal behavior through lots of input-output pairs. But in reinforcement learning, we have to learn from our own experience. So we have to create our own input-output pairs based on a reward feedback. We may also have a stochasticity and this notion of lifelong learning, infinite horizon MDPs. But for the talk, I'll focus on the finite horizon simple reinforcement learning. But a lot of topics will apply to more complex variants. Because of the way the problem is set up, usually the objective functions are different, but both of the objective functions try to estimate the difference between the optimal policy and a parametric policy. And at the end of optimization, we are hoping that our parametric policy converges to the optimal policy. So there has to be a lot of similarity because of this similar goal. In supervised learning, one of the classes of problems is called the structured output prediction, for example, sequence prediction. And one dominant approach these days is optimizing conditional log likelihood. In reinforcement learning, as I said, I would focus on finite horizon DAG environments for the talk, and we often optimize expected reward. Now, one key observation is that if we add entropy to the expected reward objective, and this is often done to encourage exploration, we can connect the dots and see that both of these objectives represent a KL divergence in two different directions. Consider the image captioning problem, where if we are in a supervised learning scenario, we call it an input image, and the output comprises a sequence of characters, for example. If we are in a reinforcement learning setup, we call it a state, and the sequence of characters is called an action or an action sequence. And in the reinforcement learning setup, the environment provides us with a reward. But even in the supervised learning case, we want to optimize a reward, which is usually based on the similarity of the emitted outputs and the correct outputs. And the real world is really a hybrid of the two paradigms. You usually hear from reinforcement learning folks saying that this is much more similar to the way humans learn, and AI will happen through reinforcement learning. But in real world, we have collected a lot of training data, and we've labeled tons of images and sentences, so we may as well use these labels and hopefully speed up the learning process. Now, I use boldface A to represent a sequence of actions, state S, and reward of S and A. Our goal is to maximize the reward of S and A. Now, we use a model or a policy that puts a distribution over action sequences. We usually use chain rule to represent the first action given the state times the second action given the first action and the state, and so forth. So we really want to put a probability distribution over a tree, which means that each action sequence has a probability and they marginalize to be 1. And we have an optimal policy that is often a one-hot distribution over the best action sequence. So the best action sequence has a probability of 1. Anything else has a probability of 0. So we can define this empirical reward objective, which is basically given a parametric policy pi theta, we find the argmax action sequence, the best action sequence according to our model, and then we measure the reward. And then we sum over all the states, or we do an expectation with respect to states. So we call this empirical reward objective. Why can't one directly optimize the empirical reward objective? What's the challenge there?
Too sparse. The reward is too sparse.
The reward may be too sparse. Yes. Anything else? Say it again.
Not differentiable.
Yeah. So the reward is not differentiable with respect to its second argument, because our action sequence is discrete. So we can't take the gradient of theta, take the gradient of the objective with respect to theta, and take that through the argmax operator. Another challenge is that the argmax may not be trivial or tractable, right? Because, for example, if we have an R and N to represent these distributions, finding the argmax is challenging, but we often resort to approximate techniques. So the key issue is the differentiability. And in the supervised learning world, people have come up with lower bounds for this objective in the structural SVM framework and directly went for optimizing that. In the reinforcement learning literature, people have come up with this stochastic variant of this objective, which is the expected reward objective. Now, in the supervised learning framework, we assume full access to the reward function. And we assume access to the globally optimal action sequence, which I denote A star. And our reward is usually the similarity of my action sequence and the correct action sequence through edit distance or blue score or things like that. In reinforcement learning, I do not have full access to the reward function. So I have to probe the reward function by asking different action sequences, and we care a lot about sample efficiency. But in the model-based RL setup, we often assume we have full access to the reward function, and some of the ideas in supervised learning would be directly applicable there. Now, in the first part of the talk, I'll try to describe how supervised learning optimizes a KL divergence between the optimal policy and the parametric policy, and reinforcement learning optimizes a KL divergence between the parametric policy and optimal policy. I use the color blue for the optimal policy and the color red for the parametric policy that's being optimized. Okay, let me go through the background relatively quickly. Entropy measures the uncertainty of a distribution. We have a distribution over action sequences that measures the number of bits to communicate the uncertainty. It's a concave function on simplex. So if we represent our distribution in terms of values that sum to 1 and that are greater than 0, then it's a concave function. When we have n actions, the maximum entropy is log n, and its minimum is 0. So if we add entropy to our expected reward objective, we would not like the one-hot distribution as our optimal policy, because the one-hot policy has the minimum entropy. So adding the entropy to expected reward often encourages soft optimal policies that are not one-hot and basically hedge their bets across action sequences. Now, KL divergence or relative entropy is an expectation with respect to the first argument of the difference of log probabilities of the first minus the second argument. It's a non-negative asymmetric function, and it's 0 only if the two arguments are equal, and it has a unique minimum. And we can write the KL divergence in terms of negative entropy of the first argument plus a cross entropy, which measures the expectation of the second argument with respect to first argument. Now, KL divergence is convex on the simplex with respect to the first argument, and it's convex in the logits of the second term. It's kind of weird, because if we represent the distribution in terms of simplex, then the first argument, which is entropy, sorry, the first term here is concave, negative of it is convex. The second term becomes a linear function of the distribution. But if it's represented in terms of the logits, what we often do with neural networks in terms of an exponential family, then it becomes convex in the second argument, and it's not convex in the first argument. And finally, this is one of the most important slides. These images are taken from Chris Bishop's book. If our reference policy, the blue distribution, is bimodal, and if our parametric policy is unimodal, and we optimize KL between P and Q, between the blue guy and the red guy, then we see this mode-seeking behavior. Because we are sampling from the blue distribution, and we are measuring the log of the second distribution. So if the second distribution ignores one of the modes, it has to pay a very large penalty. Whereas if we define the objective in terms of the KL of the red guy versus the blue guy, then we are sampling from the first argument. And if we ignore one of the modes, we are not penalized as much. Okay? So because in reinforcement learning, we want to sample from the model, we don't have any set of training data to sample from often, then optimizing KL between P and Q makes more sense, and that is mode covering. And because in supervised learning we have a data set, or we have an optimal policy to sample from, the first KL between P and Q is easier. And that has a mode covering. So I think, I don't know if...
Just a question.
Go ahead.
How does this behavior change depending on the width of the two modes?
So obviously, if the width of the modes is large and you have a lot of overlap between the modes, then it becomes a question of which one of the...
No, I mean, if one mode is very shallow and the other one is actually very wide, like, is it going to prefer one or the other?
I think there is the issue of local minima as well. So if you initialize from the basin of attraction of one of the modes, it may be impossible to use gradient descent to go towards the other mode. But if you measure the value of KL for the larger mode, it's going to be better to cover that mode versus the other mode. But it depends on the initialization as well. So here I have a typo in the slide. This is the mode covering, and this is the mode seeking. Okay? All right, so in the first part of the talk, I'm going to talk about a supervised learning algorithm that we call RAML. And the idea is to learn from good mistakes. And now we may have the image captioning problem, we may have a image segmentation or translation problem. In all of these cases, we are trying to optimize our reward feedback between, or similarity metric between the ground truth sequences and the predicted sequences. And the dominant approach is to just optimize conditional log likelihood and ignore any notion of reward. So in this setting, we have a path that's the optimal path, and we can compute the probability of that path using a neural network or an RNN. And after the fact, we can use beam search to find the argmax. And the objective can be written in terms of the probability of the best path. Okay? The probability of the best path can be written as a KL between the one-hot distribution, the optimal one-hot distribution, and the parametric distribution. And if we optimize this objective, we get back a one-hot distribution that puts all of the probability mass on the correct path. Now, there is another approach, which is optimizing the expected reward objective plus some entropy term. Okay? In this variant, we'll sample from the model and measure the reward for that path, and we also add an entropy over the policy. Now, to optimize this objective, we'll use the reinforced trick to estimate the gradient of the objective. Gradients are high variance, training may be slow, and one needs to bootstrap from a conditional log likelihood trained model for structured prediction tasks. So if we just try to optimize with expected reward, it's rather difficult because we often have a sparse reward, and the model has to find the correct sequence and then optimize for those correct sequences. And given that we have expert trajectories, given that we have the correct path, it seems dissatisfying to just sample from the model. But the key observation here is that this particular objective, the entropy regular as expected reward objective, has a optimal value at this soft optimal policy. If the temperature is 0, that corresponds to the usual expected reward objective with no entropy, right? As temperature goes to 0, the effect of the entropy term goes to 0, and we just have expected reward. I could have multiplied the entropy term by tau and didn't divide the rewards by tau, but it's more convenient mathematically to do it this way. But as temperature goes to 0, the optimal policy goes to one hot distribution. But more generally, when the temperature is larger than 0, we can show that the exponentiated reward distribution is the optimal policy. We call this a soft optimal policy. And the intuition is that because we've added entropy, then we are not satisfied with the one hot distribution anymore. And we are associating a probability exponential with the reward with each action sequence. Now, to show that this soft optimal policy attains the global optimum of expected reward, we can rewrite the expected reward objective plus entropy in terms of a KL divergence between the model and the optimal policy. So maybe we can go through the derivations here. What we've done is that we've added and subtracted this log z, which is the normalizer of the soft optimal policy. So that is sum over exponentiated reward of all action sequences. The sum over all action sequences of exponentiated reward. And the log z comes out of the expectation because it's constant with respect to the sampling distribution. And we can rearrange terms, and this gives us back the KL divergence between pi theta and the optimal policy. Okay? So because KL has the characteristic that it attains its unique global minimum at the place that the two arguments are equal, then the global optimum of this objective will be the soft optimal policy. Okay? And you see this in inverse reinforcement learning as well. Now, our idea is to more directly optimize for soft optimal policy. Right? We have the reward function for all of the action sequences. If we optimize the expected reward plus entropy term, we'll converge to this soft optimal policy. Why not optimize the reverse KL between the soft optimal policy and the model distribution? Okay? In this case, the objective becomes a simple cross entropy between the optimal policy and the model distribution, and we draw samples from that pi star and then optimize the corresponding log probabilities under the model. So it's similar to conditional log-log load in the direction of KL, and it's similar to the maximum entropy expected reward in the optimal policy. And what will happen in practice is that we have to sample from the optimal policy instead of sampling from the model distribution. So if we will talk about ways to sample from the soft optimal policy in the next slides. The temperature controls the concentration of the optimal policy, and this objective is now convex in the parameters for a log linear model. So if I just have a single layer neural network, then this objective will converge to its global minimum via gradient descent. Any questions? Now, in practice, for these structured output prediction problems, we have a similarity metric that measures the reward function for any action sequence A. So we sample from the exponentiated similarities scaled by temperature, and we have to sample from this stationary distribution pi star as opposed to the non-stationary distribution pi theta. So we don't need to worry about variance or baselines. There is no scalar multiply of the gradient. Usually those scalar multiplies that are reward increase the variance, whereas in this case you have the sort of the optimal scenario where there is no scaling of the log policy gradients. And this objective tries to distill the knowledge of the reward function into the model. So the model has to know whether this action sequence is better than the other action sequence, as opposed to just memorizing the correct action sequence. So if I don't have a lot of training data, then the model will learn to know this translation is better than this other translation, even though none of them is perfect. So that makes it much better as an objective for generalization, because the structure of the reward function is captured in the model. Now, for a particular case where the similarity between the sequences is defined in terms of Hamming distance, we can exactly sample from the exponentiated reward distribution. And you can verify that by noting that the Hamming distance takes values between 0 and the length of the sequence. So you have m buckets. If the length of the sequence is m, you have m buckets of Hamming distance. And you can do a counting of number of sequences within each bucket. So given the reference sequence, how many sequences are at a distance of 0? Well, 1. How many sequences are at a distance of 1? Well, I can select one of the characters or one of the words, and I can randomly swap that. So that's size of vocabulary minus 1 times m, which is the length of sequence. And then with the same argument, you can do a counting of the number of sequences at a distance of x. You first choose the positions that you want to change, and then you randomly change them. So for this particular case, we can do a stratified sampling to find a sequence at a particular distance. For edit distance, we presented an approximate sampler in the paper, but more generally, one can learn a model of the reward function offline. Basically, one can learn a model for the soft optimal policy, maybe even using policy gradient or any other technique, and then after the fact, apply that to the problem. Or one can do Metropolis Hastings to sample from the reward function from the soft optimal policy. But in the second part of the talk, I'll talk about an important sampling trick where we sample from the model distribution and then reweight using the exponentiated rewards. So we applied this to TIMIT, which is the MNIST of speech recognition. And we saw some significant gains. So here we report the results for the development set and the test set in terms of phone error rate. And we vary the temperature, which is the amount of augmentation or the concentration of the sampling distribution. And we see that consistently the performance improves. We want to minimize phone error rate. And then at some point, it's not worth it to sample augmentations further. And this plot is more interesting, which shows the amount of augmentation. So we are applying a whole lot of augmentations for sequences of length 20, I believe here, and the temperature of 0.85 is applying a lot of augmentation. For example, at temperature of 0.9, we are doing 5 to 9 edits with probability of 0.1. I thought 0.85 was the best temperature, but yeah, so 0.9 is the best temperature. So this is the amount of augmentation that's being applied during training, and it's even surprising that the model is learning from so many augmentations. If you think about these RNNs trained only on the correct sequence, one issue is that during training, you only see correct prefixes. But at test time, you're seeing a new input sequence, and you may go off the rail because you're not prepared for mistakes by the model. But if you train the model by augmentations, then it's prepared for some mistakes from the model itself. We applied it to a larger data set. This is WMT English to French, which is a relatively large translation data set. And we observed relatively significant improvements in terms of blue score, again, consistent across different temperatures. There are some similarities between this and label smoothing. If you have only a classification problem, then this augmentation amounts to sampling wrong classes with some probability epsilon and sampling the correct class with probability 1 minus number of wrong classes times epsilon.
So it looks like you have your temperature as a hyperparameter. Could it be a learned thing so that in certain contexts you know to explore more?
That's a good question. So we could take the gradient of the objective with respect to temperature as well, and we could optimize that. The danger is that you can overfit to the training set and find the temperature of 0, which is basically memorizing the training set.
But you put some regularizer on it.
But maybe we need a prior over the temperature. But that's a good idea. We didn't do anything in terms of picking the temperature automatically. And there is another paper that we were informed about after the paper was published. This is an unpublished work of Volkovs et al. And they apply a similar loss function to conditional random fields. And they have more baselines, and they also observe a consistent improvement. But they don't see any connection to RL there. Now, in terms of follow-up work, there is one paper by Koyamada et al. That discusses the notion of alpha divergence. So I like this figure from this plot from the paper that discusses maximum likelihood estimation as alpha divergence at alpha equals 0, and then reinforcement learning or expected reward objective at alpha 1. And then there is a whole lot of divergences in between, which is parameterized by an alpha between 0 and 1. So one can smoothly transition from the maximum likelihood estimation to expected reward objective. And there are some alternative approaches as well that I include for completeness. But now I want to move on to RL, unless there are any questions.
Regarding choosing the temperature, wouldn't it always be easier for your training set to just have the temperature be 0? Wouldn't that be the easiest loss function to learn? Yeah.
Yeah, I think so.
Okay, but you could maybe do it by backpropagating from dev set error or something, and then you could figure out the appropriate temperature.
Yeah, I don't have a good intuition of what would be the difference of KL divergence for different temperatures. Because now you're comparing two different KL divergence in terms of their optimal policy. And off the top of my head, I would imagine that temperature of 0 would be the smallest, but I may be wrong, so I'll have to check that. All right, so how can we apply this idea of optimizing the mode covering KL divergence to reinforcement learning? Obviously, it's a very attractive idea because we know that reinforcement learning can fall into local minimas, and we have a supervised learning machinery for optimizing the cross entropy or conditional log likelihood. And there exist papers in the literature, such as cross entropy method and reward weighted regression, that try to bring this supervised learning to reinforcement learning. And we also propose a new technique that we call UREX, underappreciated reward exploration. And the goal is to use the mode covering KL to perform better exploration. When we just do entropy regularization, that is promoting exploration everywhere. And it's very undirected. Whereas if we were able to somehow use the exponentiated reward distribution, if we were able to adjust our exploration towards larger reward regions, maybe that can let us succeed in high-dimensional action spaces with sparse rewards. And here is the idea. The idea is to replace the entropy term with this cross-entropy term, which is the reverse KL. Okay? So by comparison, in entropy regularized expected reward, we have entropy here. Here we have a cross-entropy, which is sampling from the optimal distribution. And we can't sample from the optimal distribution, but we could sample from the model and then perform importance sampling. Okay? So that's the gist of the idea. I should note that we apply this only in the contextual bandit setup, where we observe the reward at the end of the episode, and there is no intermediate reward. Now, the application of this to RL still hasn't been done, and I think it's interesting to think about that more. So that's future work. Yes?
I guess I'm confused. You were talking about how, okay, so we can't sample from the pi tau star, but how do you get the importance weight, like the pi star, like I guess the probability under pi star of an action?
Oh, so if we don't want to compute the probability itself, we know the reward for each action sequence. The only question is the normalization factor, right? If we don't want to estimate the normalization, the log z, then that's OK. So we can compute the unnormalized log policies. Sorry, log probabilities of the soft optimal policy.
Okay, and then normalize it, like.
Yeah. So let me talk about that here. I mean, let me just give me one slide to go over the baseline, and then I'll talk about that later.
Okay.
So just for completeness, this is the baseline. We have entropy regularized expected reward. It's very much like the usual reinforced algorithm, except that we have a entropy bonus. So you can think of this entropy bonus as an extra reward. If we sample an action sequence that's very unlikely, we give it some reward. We don't let the training process to kill all the unlikely action sequences. Okay? And if you optimize this objective, you get this soft optimal policy, right? And in practice, we observe that this works better than reinforced. We are not the first to observe this. In fact, Williams and Peng proposed this in 1991, but then it's adopted more lately by Menih et al. And later on by almost all of the policy gradient algorithms. Now, what would be the training process for UREX? Well, we would sample KIID samples, action sequences A superscript K, and we would compute the scaled reward for those action sequences, and then we would subtract the log policy of the current model. Okay, so there is this thing called self-normalized importance sampling, where each set of importance weights are normalized. And this is biased, but usually has a much lower variance. So this is what we do. So we don't have to compute the normalization because of the self-normalization that's happening through the importance weights. And instead of the entropy bonus, we'll have the Eurex bonus. That is the importance weights, right? So what's happening here is that we are trying to calibrate the scaled reward values with the log policy values. When we are at optimal point, at optimal policy, these values are equal for any action sequence. Basically, the difference is equal for all of the action sequences, right? But when we are not at the optimal, there may be an action sequence AK that has a moderate reward. It doesn't have to be a very large reward, but the model underestimates the corresponding reward, right? And that is the idea of underappreciated action sequences. So if there exists even a tiny reward, but the model doesn't associate a calibrated log policy for that action sequences, for that action sequence, then that action sequence can win the competition between the K action sequences that are drawn from the model. And we call that action sequence the most underappreciated action sequence. Does that make sense? Do you see the intuition here? So with a lot of previous work, they would just sample from exponentiated reward, or they would take a top K buffer of the best action sequences. The problem with that approach is that it's very greedy, and it's kind of mode seeking again. So it's trying to add a mode seeking term to the policy gradient if we were to add those two terms together. But in this case, somehow automatically comes out of the model that we have to explore underappreciated rewards. So we applied this to algorithmic tasks from OpenAI Gem. And in practice, we observed that at the beginning of training, the importance weights have a large variance. But after a while, the variance gets small, which means that all of the importance weights are relatively the same. And that is when the reward goes up. That is when we kind of solve the task. We observed consistent improvement over the entropy regularized expected reward across the algorithmic tasks, and we can even solve multi-digit addition and binary search by just providing the return at the end of the episode. But we use curriculum learning. That's important. All right. If there isn't any question, let me jump into the more interesting part. Any question? Yes?
Is it possible to compare Eurex to like the Dan and Hinton expectation maximization for RL kind of thing? Because the relationship between the likelihood and the temperature reward seems similar.
Yeah, I think there is a lot of similarity there. But I don't think they've proposed this objective of adding expected reward to the log likelihood term. So we are kind of doing them simultaneously. But this particular objective is novel. But yeah, so there is a lot of connections to some of the earlier work on inverse reinforcement learning as well. All right, so in the third part of the talk, I'm going to talk about an algorithm called path consistency learning, where we discuss the characteristics of entropy regularized expected reward in a full MDP setup. Because so far, we were considering simplified reinforcement learning algorithms or bandit algorithms where we only have a total reward in the end, either in the supervised learning case or in the reinforcement learning case. In the talk, I'll only consider finite deterministic MDPs with DAG structure. So I can do induction, okay? But all of the equations apply to the more general MDP case. You can read the paper for that, but it's kind of nice to consider this setup and get some intuition. So we are at a state S, 0, and we have n possible actions, each of which with some reward. A1 with reward of R1, and we are optimizing policy 0 of A1, okay? And what we are trying to do is to estimate the value of state S0, assuming that we have access to the values of state S1 to Sn, okay? That is kind of like a dynamic programming induction setup where we assume we have, for example, perfect values of the state S1 to Sn, and then we try to induce the optimal value of S0. If we consider the expected reward objective, we can write the objective in a recursive way in the following manner. So the expected reward for S0 and pi measures the expected reward under the tree of S0, okay? And then we can recursively write that in terms of the expected reward of Si for I between 1 and n. Is everybody happy with this? Now, assuming that we have access to the optimal value of S1 to Sn, that's defined in terms of the maximum expected reward over policy. So this is the definition of V superscript O, the optimal value. Then we can rearrange the objective in terms of basically optimal value, right? We can get rid of all of these terms, the expected reward terms for Si, and replace them with optimal value for Si, okay? And then the optimal policy becomes the one that puts all of the mass on the maximum reward plus future value, right? Discounted future value. And then if we substitute the optimal policy into the objective, we get this backup operator, right? This is the usual optimal Bellman operator that takes the max of the reward plus value for the subsequent states, and then backs it up to each state. And you can show that this is a contraction map and prove this for general MDPs and a stochastic setup as well. Now, suppose we have entropy regularization as part of the objective as well. We can write the objective in terms of an expectation over reward minus temperature times log pi, right? If you take the log pi out, that is the entropy term. And if you take the reward term out, that is expected reward. And then you can recursively compute entropy and expected reward, right? So this is not quite entropy, but it's the notion of discounted entropy, because entropies of successor states are going to be discounted by gamma, right? Now, what happens if we try to do induction for this objective? Well, let's suppose we use V star to denote the optimal value at a state that is attained when we maximize over pi of the entropy regularized expected reward. Then, given our initial derivatives about the Boltzmann distribution and exponentiated reward distribution, we can see that the optimal policy for a state is going to be determined in terms of exponentiated reward plus discounted future value, right? And then if we substitute that optimal policy back into the equations, we get log sum x of the reward plus future discounted values. This part, I think you'll have to do offline. It's just some algebraic manipulations, but you'll get the softmax backup operator. Softmax in terms of log sum exp. And this is the backup operator, where we don't take the hard max, but we proportionally consider all the future states and actions and back up this log sum exp term to update this state and the value at the state S0. Now, in the paper, we show that this is a contraction map as well, and it works for general MDPs. But for DAGs, I think this would be a proof for the optimality of the state values. Now, some of these observations have been made by previous work as well, even though I don't think in this clean manner. Now, the main contribution of our work is to realize that we can rewrite the optimal policy in this way. So note that previously I wrote the optimal policy is proportional to exponentiated reward plus discounted future reward. But the normalizer of that distribution is log sum exp, right? So we have to, is exponentiated log sum exp. That is exponentiated optimal state value at a state S, right? So here I'm writing the equation for a successor state S prime for state S, so I'm changing the notation a little bit. And I'm claiming that the optimal policy is again the exponentiated reward distribution, or the soft optimal policy, but the normalizer of that policy can be obtained by the state at the, but by the state S, by the value at the state S. Okay? And if we take the log of both sides and we rearrange terms, we get such an interesting connection between the state values and the policy. So what this says is that the state value at the root should be related to state value at any of the successor states in terms of the reward on the edge minus tau times the log policy of the edge. And this is correct for any of the edges, right? It doesn't have to be the optimal path, or it doesn't have to be the samples from the model. For any trajectory or for any pairs of states, this has to hold. Now, more generally, we extend this to multi-step consistencies where we have a sequence of states from S1 to ST. Again, I'm changing the notation. And I just add the consistency terms for pairs of successor states, and you get a telescopic cancellation effect, and you're left with this consistency. So these terms within the squared error has to be 0, right? Meaning that the difference of the state at the root with any of the states that's t edges below relates by some weighting in terms of the discounting factor of the rewards on the edges and the log policies on the edges, right? And if temperature is 0, this is kind of like Q-learning, but it's some twist. I mean, maybe I shouldn't have gone to the temperature 0 case. Things get a bit complicated there. So these consistency equations hold for on-policy and off-policy traces. And what we do in practice is that we have a model of policy, pi star, and we have a model of Q values or state values, and we optimize the inconsistency error by gradient descent. Right? So it's kind of a squared error on the soft consistency terms. And in practice, we compare against DQN with prioritized experience replay and A3C. And on the algorithmic tasks, we observe pretty significant gains. But importantly, we can also add expert trajectories because these consistencies hold for any path. So we can add expert trajectories to our replay buffer, and we can also optimize the consistency on the expert trajectories. And we see much more significant gains if we have some correct traces of the algorithmic task. Now, I should note that there is extensive work related to PCL, including work by Kappen, Zibart, and Azar. And there are a few concurrent work as well, one by Harnoja et al. And one by Schulman et al. And there's a discussion of the gradient of these PCL consistencies and how they relate with Q-learning and actor critic. But I wouldn't go into the details in the interest of time. Now, we tried to apply PCL to continuous control because we felt that the algorithmic tasks aren't the tasks that most people care about in oral. So we thought, what if we apply PCL directly to continuous control? And in that case, the policy that we use is a Gaussian policy. Okay. But interestingly enough, the PCL didn't perform very well on algorithmic tasks. And we thought that most likely one of the reasons is the instability of training, especially when we use off-policy traces. And TRPO is known to produce stability by penalizing the KL divergence between the previous policy and the current policy, right? And there is a family of RL algorithms before TRPO as well that try to make sure that the policy is not updated too much. So the idea here is that we have a baseline policy pi tilde, and we have a parametric policy that's being the current policy is pi, and we try to add to the expected reward objective a KL divergence between pi tilde and pi. Okay, but algorithms like TRPO require second-order optimization to estimate the Fisher information matrix that would in turn approximate the KL divergence. We made a very simple observation and a very useful one, which is that if we penalize the reverse KL between the current policy and the baseline policy, then all of our consistency terms can be updated. Okay, and let me go into the derivatives right away. So this is the way I used to write the entropy regularized expected reward, but now I'm adding another term, which is the KL between the current policy and the previous policy, right? And I have one coefficient tau for the entropy. I have another coefficient lambda for the KL divergence. Now, when you think of the KL divergence between the current policy and the baseline policy, that has an entropy term. So now the total coefficient of the entropy will be tau plus lambda. And it has a cross entropy term that is between current policy and log of the baseline policy, pi tilde, right? And the violet term that is the cross entropy can be thought as a constant reward, right? So intuitively what happens is that if I take an action that was highly probable according to my previous policy, then that is going to add some reward to that action. It may be that my current reward somehow doesn't capture the importance of that action because there are some future rewards that are backed up in my previous policy. And this is kind of serving as a pseudo reward for my actions and action sequences. Now, we can rewrite the consistency term that we had it early on, and the only difference is that another term, another log baseline policy will be added to the consistency errors, right? And we can write these consistencies in terms of single step backup or multi-step backup. Okay? So now we have this stable algorithm that we call trust PCL that basically updates the policy once in a while. In practice, what we use is a momentum term that basically updates the parameters in a strange way. So if we have theta t as our current parameters, then we define theta bar t or theta tilde t in terms of, for example, 0.1 theta t and 0.9. So this is going to be theta tilde t plus 1. That's going to be 0.9 theta tilde t. Okay, so it's kind of a lagged momentum term that slowly adds the new parameters to the old parameters, but it has a bias towards keeping the parameters stale. And you can control this parameter to affect how much delayed your baseline policy is. And simply we add this reward to this pseudo reward to our usual rewards. Now, I want to make a distinction between the role of entropy and relative entropy. The entropy terms are there to enable exploration and prevent the model from concentrating on a few action sequences. But the relative entropy is there to provide some stability in terms of controlling the amount of update to the model parameters. There is another way of thinking about the role of relative entropy in terms of the information geometry of the optimization, right? So when we do stochastic gradient ascent, we are assuming a Euclidean geometry, which is optimal by following the gradient direction. But if we care about another notion of reward, another notion of the objective in terms of, for example, KL divergence, we may as well define the information geometry in terms of the objective itself and the relation of the objective with respect to parameters. And the Fisher information matrix provides a particular parameterization of the information geometry that's optimal for log likelihood. And we have to approximate it through all sorts of approximations. But in practice, we can just apply the KL, the relative entropy between the current policy and baseline policy as a proximal term, and it works very well. I should note that we have a automated way of setting the lambda, that is the effect of that is controlling the effect of relative entropy, and I encourage you to read the paper for the details of that. That's kind of important, how quickly you change the effect of relative entropy. At the very beginning, you don't want a lot of bias towards the previous policy, because that's kind of random. But towards the end, you want to magnify the effect of the relative entropy term. And we don't have deep insights into which one of the two relative entropies is important. We talked about KL divergence in two directions for supervised learning and reinforcement learning. For the relative entropy term that provides a stability, I would just leave it at mathematical convenience. It works very well in our framework that we sample from the policy and then evaluate the log policy of the baseline. This is different from most other papers that use the reverse KL for the relative entropy. And we expected that this form of policy learning should enable us to capture multimodal policies and maybe even go beyond Gaussian policies. Because in practice, Gaussian policies seem too restrictive for continuous control. And we did a lot of experiments with other forms of policy, energy-based policies, and things like that. But we found that for Mojoko tasks, at least, the Gaussian policy is sufficient. There is another point here that I want to mention, and that is that when we optimize expected reward using policy gradient techniques, then the expected reward is optimized, right? So if we look at the expected reward of the policy, which is basically drawing action sequences with probability according to the Gaussian and adding some noise to the action sequences, then the expected reward is optimized during training. And when you compare techniques, then usually for the policy-based techniques, for the policy gradient-based techniques, the expected reward is higher. But what we really care about is the performance of the algorithm under greedy actions. We don't want to randomly draw samples from a Gaussian that may end up giving us lower rewards. So we want to just go through the mode of the Gaussian or the mean of the Gaussian. And we observed that there is a big difference for PCL between the expected reward objective versus the reward for the greedy actions. And we report the results for the greedy actions. I think that makes much more sense. It's also documented in the literature that if you use Q-learning, for example, the reward of the greedy actions will be higher than the expected reward, because Q-learning is not really aware of the expected reward objective much, and the consistency terms are optimizing in some other domain. This is the results slide that I have on Mojoko tasks. The x-axis is in terms of the millions of steps, and we have a knob that can control the amount of off-policy data versus the amount of on-policy data within the trust PCL algorithm. And here we draw two different curves of trust PCL. One is that has more sampling from the off-policy data, and the other is more on-policy. And we observed that at least they're competitive with TRPO, which is a state-of-the-art technique for continuous control these days. This is our own implementation of TRPO, so we can control hyperparameter tuning quite a bit. And at least there needs to be more exploration in terms of empirical analysis. I should point out that I'm not happy with the quality of our empirical analysis for continuous control. Unfortunately, we don't have held out tasks and we don't do hyperparameter tuning. So here we do what everybody does, which is like hyperparameter tuning on the particular task that we're optimizing. And I should point out that because of this effect, which is there's no training versus test split, we often need to anneal the temperature towards 0 because we want to really overfit to the training task. But in the supervised learning setup, we weren't annealing the temperature because we wanted generalization to test cases, and we didn't want memorization of the training. Here we have a table. You got to take this table by a grain of salt because we're comparing different code bases. The TRPO that's marked as ours and the trust PCL, these are our own implementation. And we report the best average reward in the first 10 million training steps. We observe that trust PCL achieves very good results, even in comparison with the reported results in the literature. So I'd say only in Walker 2D, we are not achieving the best results. But again, this is kind of arbitrary, depending on how much hyperparameter tuning you do and what you report at the end of the day. Do you average over seeds? Do you select a bunch of seeds out of the seeds that you tried for training, etc.? All right. If you have any questions before wrapping up, please interrupt. All right, so in summary, we discussed this notion of soft optimal policy that hedges its bets across different action sequences rather than only picking one action sequence. And we showed that how conditional log likelihood is a KL between the soft optimal policy and the parametric policy at temperature of 0, and how expected reward is the reverse KL at temperature of 0. And then we advocated going beyond temperature of 0, either by adding entropy, and that's what's done in the literature quite a bit, or by going towards the soft maximum entropy estimation by augmenting the ground truth sequences. We also proposed a more reasonable exploration strategy that tries to incorporate the mode covering behavior of the KL into reinforcement learning. I think this is probably one of the most important topics for the future of RL, how we can somehow come up with better objectives. And it's kind of surprising because even in the entropy case, when you think about it, we are optimizing expected reward, right? And we take its gradient. But somehow we add an extra term and we optimize, and we again measure expected reward, and we do better. So we optimize an auxiliary objective, which is not the objective that we care about. And somehow that achieves better expected reward. And I think this is mainly because of the non-convexity of the problem and the abundance of local minimas that wasn't as much of a deal in the supervised learning setup. So we need to come up with better ways to tame this optimization problem and encourage covering modes, encourage search and exploration. I guess exploit dilemma is not something new, and we have to come up with better ways for exploration. And then at the end of the talk, I talked about how to bootstrap optimal state values and optimal policies under entropy regularization. And then we talked about a way to add relative entropy and trust region to the PCL algorithm by incorporating the relative entropy between the current policy and the baseline policy. And now I can take any questions about any of the topics. Yes.
So you said, what kind of maybe like environments besides the Joker that you think could be good for like kind of like non-Gaussian or like unimodal policies?
I guess you gotta take a look at Thomas's paper from Sergey's group. I think one of the interesting insights that they had in that paper was basically multitask learning and training on one task and trying to generalize to a new task. And I think in that environment, if you just optimize a narrow Gaussian for your particular task and you don't know what's going on elsewhere, then you're in trouble. Whereas if you have a energy-based policy that kind of like the soft optimal policy assigns a probability proportional to each reward for each action sequence, then you're much more likely to succeed at generalizing to new tasks. So that's my insight. But I think you got to look at the deep energy-based reinforcement learning on deep energy-based policies for a better treatment of that topic. But I think, we got to come up with better baselines and better benchmarking of RL algorithms because that seems to be very important, the multitask aspect and learning on a whole bunch of tasks simultaneously rather than just optimizing for one task and even doing a lot of hyperparameter tuning for each task.
So at one point you mentioned that I think you tried RAML or UREX on the continuous control tasks and it didn't work well? Are you talking about RAML or UREX?
I think one issue, first of all, when we were developing when we were developing UREX, we applied just the cross entropy term to this sort of these contextual bandit problems. And we observed that that doesn't work very well, I think mainly because we are doing importance sampling, and if the proposal distribution is crappy, then it's very difficult to push that proposal distribution towards succeeding, towards becoming a better proposal distribution. So that's one point. But I had a collaborator that started working on UREX for continuous control. So we didn't use replay buffer within UREX. That's a shame. So we just used on-policy samples to do the importance weighting. And there are ways to have a replay buffer and sample from the replay buffer to estimate the exponentiated reward distribution. Obviously, you gotta be careful with respect to the variance of importance weights. But that's one direction that we really didn't explore much. But I think the more important direction is accommodating partial rewards. And in the UREX setup, we just sample, and then at the very end, normalize. And one can think of better sampling scheme, sort of like particle filter sampling schemes where you resample your particles according to your rewards, your partial rewards so far, and you even consider a model of the state values. And that's something that we had been thinking for a while, but we never really tried that.
You mentioned, I think, for the RAML objective, the one-layer nets have a convex objective.
Yes.
Did you guys take a look at how those, like the one-layer nets compared to, I don't know, did you run the experiments on, what kind of architectures did you run them on?
No, we did try the sequence-to-sequence architecture that has an embedding layer and a whole bunch of RNNs and stuff like that. But one can think of convexity for a single layer model in terms of convexity with respect to the last layer of neural net. So at any given time, whatever set of parameters I have, if the objective is convex with respect to the last layer, I think that's a very good thing because hopefully the last layer will be optimized much more efficiently. But basically this whole notion of more convexity, relative convexity of objectives and stuff like that is something that is interesting, but I think it's a difficult topic. But it seems like if the objective is convex in the last layer, maybe the full objective of the neural net is more convex. But what that means, I don't know. I think some optimization folks are looking into problems like this, but I'm not very familiar.
And you did the sequence-to-sequence thing because Unravel it was for the algorithmic tasks, right? So those were the benchmarks.
So the structured prediction problem, we had, for example, translation using a sequence-to-sequence model. For the algorithmic tasks, we also used an RNN architecture. It was a much simpler architecture without attention and stuff like that. But yeah, so you can think of that as a sequence-to-sequence architecture as well. Yeah, we didn't consider linear models, but I think it's interesting to study that problem some more and maybe think about how the other direction of KL can help in that direction. Anything else?
Did you ever try incorporating demonstrations into Trust PCL the same way that you incorporate kind of good data in PCL for the algorithmic examples?
I think we did to some extent, not exploring it too much. But I think before one of these deadlines, we did try a week or so, and then we give up, given the proximity of the deadline. But I think we got, yes. But I think that's something that we should do. I should point out that for the translation setup, we did something in the Google's neural machine translation paper, which is we simply added the conditional log likelihood term to the expected reward objective. So let's say we want to optimize for blue score, but we could also combine the two objectives, kind of like the alpha divergence, but in a much more hand-wavy, simpler way. You just combine the two, and that provided a relatively large gain in terms of especially stability of learning. Because if you don't use expert demonstrations, the model can slowly shift. And I think one direction is to just add those terms as a sort of cross-entropy objective to our policy gradient objectives. That may be a better way of incorporating expert trajectories.
All right, let's thank Mohammed.
All right, thank you.